So, after discussing the basic terms related to Earth's magnetism, now we are in state to define some more important terms. Those are related to Earth's magnetism as well. So far we had discussed about the terrestrial magnetism. Now we are going to discuss about the declination. Now, what is this declination? So this is basically the angle between the geographical meridian and the magnetic meridian. Here in this figure we are having this geographical meridian, and here we are having the magnetic meridian, and the angle between these two meridian is known as the declination, that is angle of declination. Now this magnetic declination arises because the magnetic axis of Earth does not coincide with its geographic axis, and it is varying from place to place here. Now the line shows on the map through the places that have the same declination are called isogonic lines. On the other hand, the line drawn through places that have zero declination is known as agonic line. Now we are having another term that is known as the angle of dip or magnetic inclination, and this is basically, from figure you can see that B represents the net resultant magnetic field due to this geographic meridian and the magnetic meridian, and we are having this angle between the horizontal of this magnetic meridian and the resultant magnetic field. This is represented by delta, and here we are having the horizontal component of magnetic field, and here we are having the magnetic component of this magnetic field. So the angle between the horizontal component of the Earth's magnetic field and Earth's resultant magnetic field is known as the dip or inclination at that place, and it is 0 at the equator and 90° at the poles. And the line drawn up on maps, geographical maps, through places that have same dip are known as isoclinic lines, and the lines drawn through places that have zero dip is known as the aclinic lines, and it is the place known as the magnetic equator. After defining these two angles, we are having another term that is horizontal components of Earth's magnetic field, that is BH, and this is that particular point of the total magnetic field in the horizontal direction. So the component of Earth's magnetic field along the horizontal at an angle delta is called the horizontal component of Earth's magnetic field, and it is represented as BH is equals to B cos delta. At magnetic equator, this delta is equals to 0°. Therefore, at magnetic equator, BH becomes the net magnetic field. And at poles, this delta becomes 90°, and this horizontal component of Earth's magnetic field at poles becomes 0. Similarly, we can have the vertical component as well, and that vertical component is BV is equals to B sine delta, and the net resultant magnetic field by using the vector law of addition is given by B is equals to square root of BH square plus BV square, and there is a law that is known as the tangent law, and according to that tangent law, if a magnetic needle is suspended in a region where we are having two magnetic field, suppose that is B1 and the field B2, in that case the needle will align itself along the direction of resultant field of the two fields at an angle theta, such that the tangent of angle is the ratio of these two fields, that is tan theta is equals to B2 divided by B1. Now after defining these important terms, we are having another term that is known as the neutral point. As the name suggests, neutral, that is void, and it is the point where the magnetic field due to a magnet is equal and opposite to the horizontal component of Earth's magnetic field, and the resultant magnetic field at the neutral point is zero, and hence if a compass needle is placed at such a point, in that case it stays in any position, so it dances like it is not showing any north and south direction. Now let us compare between the materials. After discussing the properties of the magnets, let us divide the materials according to their properties, and mainly the magnetic materials are divided into three main types. One is diamagnetic, another one is paramagnetic, third one is ferromagnetic substance. Now the diamagnetic substance, when placed in magnetic field, they get weakly magnetized opposite to the direction of the applied magnetic field. They repel the magnet. On the other hand, the paramagnetic substance get weakly magnetized along the direction of magnetic field, and examples are aluminium, chromium, alkali materials. On the other hand, the ferromagnetic substances are those substances which are strongly attracted by the magnet, and they are the nickel, cobalt, dysprosium, gadolinium, etc. Now, when these diamagnetic materials are placed in the lines of force, that is magnetic lines of force, they avoid the substance. Now you can see from this diagram that the line of or magnetic line of forces are moving apart or in air as compared to that through that substance. In case of paramagnetic substance, when they are placed in magnetic field, the magnetic field or it aligning itself in the direction of the applied magnetic field, or the lines are flowing through that substance. On the other hand, in case of ferromagnetic substance, the lines are passing through crowdedly through that particular ferromagnetic substance. Now when these substances are placed in magnetic field, they move towards the weaker field from stronger to weaker, that is repulsive nature. When the paramagnetic are placed in magnetic field, they are moving along the field weakly, and the ferromagnetic, they are moving along the strong magnetic field. Now for this first case, let us consider we are having a diamagnetic rod, and when this rod is placed in a magnetic field or suspended in a magnetic field, this rod is aligning itself perpendicular to the direction of the field in this manner. So this shows the repulsive nature. On the other hand, if a paramagnetic rod is placed in a magnetic field, in that case it is aligning itself along the direction of magnetic field but slowly. And if the ferromagnetic substance or rod is placed in magnetic field, it is aligning itself along the direction very fastly. So it shows very fast magnetization. If we are having the substances and we are having two magnets, let us discuss the first case, and a liquid diamagnetic substance is placed in a beaker, and that beaker is placed over the magnets. In that case, that material collects away and a dip is created at the center. But if the magnets are far apart from each other, then material is collecting at the center. So this shows that repulsive nature of a diamagnetic substance. But if a paramagnetic liquid is taken in a beaker and that beaker is placed over a magnet, so if magnets are closed, in that case that liquid is collecting at the center. But if the magnets are far apart, then the magnet is collecting at the pole of the two magnets and dip we are getting at the center. Same result we are getting for ferromagnetic substances as well. Now we are having some more points of difference between these ferromagnetic and diamagnetic substances, as when they are placed in magnetic field, diamagnetic substance get weakly magnetized opposite to the magnetic field, paramagnetic substance weakly magnetized along the direction of magnetic field, and the ferromagnetic substance strongly magnetized in the direction of induced field. The dipole moment is negative. For the diamagnetic, it is positive with small value for paramagnetic, and it is positive and with a large value for the ferromagnetic substance. Intensity of magnetization is negative for diamagnetic substance and positive for both para and ferromagnetic substance. And magnetic susceptibility is always less than unity for diamagnetic, and it is more than unity for the para and ferromagnetic substances. Magnetic susceptibility is negative for the diamagnetic, and it is positive for the para and ferromagnetic substance. And these diamagnetic substances do not obey the Curie law, whereas the para and ferromagnetic substance obey the Curie law. Now, what is this Curie law? Basically, the Curie law is defined as, from the experiment, it has been found that intensity of magnetization of a paramagnetic material is directly proportional to the magnetizing field intensity H and inversely proportional to the absolute temperature. So, the magnetic susceptibility of material is given as I is proportional to this H upon T, or I upon H is proportional to 1 upon T. So susceptibility is 1 by T proportional, and if we are removing this proportionality sign, we are having a constant of proportionality, that susceptibility, magnetic susceptibility is equals to Curie temperature divided by the absolute temperature, where C is the Curie constant. And the Curie temperature for iron is 1000 Kelvin, and for cobalt it is 1400 Kelvin, and for nickel it is nearly 600 Kelvin. From the graph we can see that if we are having H by T ratio along x-axis and this intensity along the y-axis, we are having a plot for that Curie temperature. So this particular portion here, the slope, this is representing the Curie law region, and this is the saturation region for a magnetic material. Now, what is the origin for this ferromagnetism? Basically, this is the dipole of the substances that is being created in between the molecules of a particular substance. After that is our next topic, that is known as the hysteresis loop or the magnetization curve. So whenever a ferromagnetic sample is placed in a magnetizing field, the sample gets magnetized by induction, and as the magnetizing field intensity H varies, the magnetic induction I does not vary linearly with this. So we can see from this graph that we are having this magnetization over H along the x-axis, and this magnetic induction B or I along the y-axis. So as we are seeing that as we are varying this field intensity from the origin or initial position, the substance is magnetized and magnetism is induced in that particular substance. Now if we are reducing this intensity, in that case it is not following the same path and it is going through this red line path. And again, if we are increasing the intensity, it is again reaching the saturation point A. Now what we are concluding from this graph, that the intensity of magnetization I increases with increase in magnetizing force, initially from position OA, and reaches the saturation at A. When this force is reduced, in that case the magnetization intensity decreases, but it is not reaching that position origin O where this magnetizing force is 0. So the residual magnetism set up in the magnetic or material is represented by the curve OB, and this is known as the retentivity of the magnetized or ferromagnetic material. Now if we further bring this intensity of magnetization to 0 to demagnetize that material completely, in that case opposite magnetic force is applied, and this magnetizing force represented by this OC, and that is known as the corrosivity. And after reaching the saturation level in opposite direction, level D, when the magnetizing force is reversed, the curve closes to the initial saturation position A, completing the cycle. So what we are going to conclude here, that we are starting from this position O, reaching this saturation and again decreasing that intensity, and reaching this saturation and again reaching this saturation. Now after here we are reaching this saturation and we are obtaining a curve OA, that is known as retentivity for a material, and this is CO, that is known as corrosivity for a material. Now through this loop we are getting that the substance is being magnetized after the removal of intensity, or there is magnetism induced in that particular substance. Hence the loop A, B, C, D, E, F, A is known as the hysteresis loop, and we are having an animation to show that we are having two types of ferromagnetic material. One is soft and another one is the hard ferromagnetic material. Now the soft ferromagnetic materials are materials in which magnetization disappear on the removal of external magnetizing field, this closing loop, and on the other hand the hard ferromagnetic materials retain magnetization even after the removal of external magnetizing field, that is this opening loop. So in this manner we can choose the material for our purpose. We can design our electromagnet like the soft iron, mu metal, stelloy, they are the soft ferromagnetic substance. On the other hand, the steel, alnico, lodestone, ticonal, etc., these are the hard ferromagnetic materials. These are used to make the strong electromagnets. With this we are concluding our chapter, this magnetism.